So, hi everybody.
You want your face or
I'll
the
just
screen?
stand in front of this and make it easy.
Okay.
All right. Hi everybody. For those who don't know me, I'm Ed. I am now a grad student, which is a scary thing for me to say. I finished my EE degree this past May, and now I am desperately trying to finish my master's while also TAing class and generally being lazy. I'm here to talk to you today about a piece of software called gSchem. So a couple things I'm going to cover today. What is schematic capture software? gSchem, as opposed to other schematic capture software. A brief introduction to Linux, since it only runs on Linux, and Linux is scary and frightening for people who aren't CS majors and don't think it's awesome. And then I'm going to actually get into using the software. So for starters, how many people here are from the freshman stages class? Show of hands. Okay, how many people here ESIS 371, 245, 210, just think circuits are cool? No idea why you're here. Okay, how many people have worked with any kind of electronic schematic software? Okay, what have you used? Eagle? I'm guessing a lot of Eagle. Altium? Altium's nice. Anything else that I'm missing?
KiCad.
KiCad, yeah, get started. So, why would you use schematic capture software for people who haven't before? So you could just hand draw all your schematics for people who read XKCD. This is the funniest thing that was ever made. And you'll end up with lots of squiggles all over the place. And if you're like some professors here, your inductors will look like resistors, your resistors will look like wires, and no one will have any idea what you're talking about. I'm not referring to any specific professors who teach any specific classes because they pay me and I don't want to insult them on YouTube. But the alternative is you could use some nice, pretty schematic capture software and get schematics that people can actually read, and more importantly, you can email to people and publish and print out and they'll look good. It doesn't matter how good your circuit is if everyone looks at your schematic and they're like, I have no idea what that is, and it looks really unprofessional. So having the ability to use software like this is valuable. It's also a skill that is used throughout industry. So if it's something you can put on your resume, even if it's a software that no one's using, and in industry they like to spend lots of money on Altium, which is $5,000 a seat. So they're not using freeware like this, but you can still say, look, I've done this, and here's my portfolio. So that's a valuable thing. So I'm talking today about gSchem, which is part of the GPL EDA suite, gEDA, which includes gSchem, which is the schematic software, a rather creatively named program called PCB, which is their printed circuit board software, and GerbV, which is for viewing Gerber files. Gerber files are the files that you would actually send to a manufacturer to make PCBs. It is completely free and open source, so all of the CS hipsters will be proud of you for using open source software. And it also means that you don't have to pirate Altium or pay $5,000. And pirating Altium is great if all you're doing is projects that no one else will ever have to see. But if you're planning to ever productize something and you've got some investor who's like, oh, so what did you make this in? You're like, I don't want to tell you because I didn't pay for it. This, no matter what you do, there are no limitations on it, and you are completely within your rights to make boards however big you want, unlike Eagle, which is free up until like a 6-inch by 6-inch board or something, and then you have to pay for it. So it's free, it's open source, all the CS hipsters will love you. Downside, it only runs on operating systems that end with X. So Linux, Unix, Mac is secretly a Unix operating system, so it will run on Macs. I think there's some voodoo magic to make it run on Macs. I don't own a Mac. I know Chris Dickey and Mike DeLibero can make it run on their Macs without booting Linux. I use Ubuntu for all of my Linux needs. That's what I'm running right now on my laptop here. And I've got a stack of Ubuntu Live CDs here, which have, so standard Ubuntu distribution obviously does not include this in it because most people who use Linux don't care about circuit design. But I've rolled some custom live CDs, and I'm calling Ubuntu EE because I'm creative and markety like that. And it has gSchem and PCB and the rest of the gEDA suite built into the live CD. So you don't have to commit to having 2 operating systems on your computer. You can just boot from the CD and play with it a little bit. And it has a very helpful wizard for if you do want to install it as a second operating system. It is nice to know how to use Linux and be able to use Linux, even if you're not a CS. So I'm going to be going into a little bit of just basic Linux stuff to make it less scary for people who've never used. Actually, show of hands, who's used Linux before? Oh, that's encouraging. Okay. If you already are a Linux user, if you use Ubuntu, you can install this from the Software Center. Just search for gEDA. You can run it on Windows, sort of. There's a software program suite for Windows called Cygwin, which lets you run Linux applications in Windows. I did this once, like a year ago, when I was like, I don't want to deal with a Linux dual boot. I want to just run this in Windows, and it was painful and obnoxious. So I'm not going to tell you how to do it because A, I don't remember, and B, it was obnoxious. So my advice to you is if you want to use this software, either own a Mac or have a Linux dual boot. Okay. So with that, I'm going to jump into a little bit of using Linux. So this is Ubuntu, for those who aren't familiar. Ubuntu is the friendliest distribution of Linux that I've ever seen. When you first start up Ubuntu, you will have a friendly desktop with some kind of pretty background. And then over on the left here will be a menu of all the things you can open. If you click on this, that's sort of your start button. And just type in what you're looking for. So in this case, we want to open up gSchem. And there it is. I've already got it open. One of the cool things about all operating systems that aren't Windows, they let you have multiple desktops. So I have 4 open right now. But anyway, there we go. So you open up gSchem, you're going to get this blank drawing. And it's got a border and a title block. So if you wanted to make a fancy printout that has all of the titles and borders and stuff that's there, the first thing I do whenever I open a new design is almost always delete this. I just selected that and hit the delete key because you find very quickly that your design doesn't fit in there. And so then you're stuck with this title block that doesn't hold your whole design. And half the time you don't want to print it out anyway. So it's a matter of preference. If you're planning on making something professional looking, you should probably keep your title block. I just get rid of it. So now we've got a blank canvas on which to design things. For this demo today, I'm going to be doing, I feel like Frank Merrick. I'm going to be doing a basic heater control. So let's say we have a little aquarium, and we've got a little lizardy guy in here. He's got a tongue. And we've got a little heater here. We want to keep him warm. In order to do that, we need some way to control our heater. So we've probably got some kind of thermometer, and it's wired into our heater, and we need to control it. Well, let's look at this in a little more detail. We're going to have a temperature sensor, which is going to output a voltage that corresponds to our temperature. We're going to have a knob, which is going to be a potentiometer, which is also going to put out the voltage. So this is our temperature, and this is our set point, which is going to be our desired temperature. So then we're going to use the magic of op amps to get the difference. So this is our, this is going to be set point minus 10. And then we're going to run out of space on this paper. Then we're going to have what is called a PI controller controlling our heater. I'm not going to get too much into the theory of how all this works, but suffice to say, you're going to get a temperature out of a temperature sensor. You're going to compare it to a desired temperature. You're going to use that to send an on-off signal to your heater to make it warmer or cooler. So if your temperature sensor says it's too warm, you're going to turn off your heater. If your temperature sensor says it's too cool, you're going to turn on your heater. So now we can actually go into the nuts and bolts of designing this thing. So for starters, I found a little temperature sensor on the internet. Where is it? How did I close it? That'd be sad. But there is, oh, there it is. So Microchip makes this product called the MCP 9700. I picked it somewhat at random, but basically it has probably a helpful graph here somewhere. There we go. So we've got this thing. It outputs a voltage with temperature. I'm looking for a graph of that. There we go. Temperature in, voltage out. So it's roughly linear, and it will tell us what temperature is at a voltage. So I made a symbol of it in gSchem, which I'll get to later, but for starters, I'm just going to do schematics. It has 3 pins. It has a power pin called VDD, a ground pin, and the output. So let's go back to, I lost it. There we go. Go back to gSchem, and so we want to add a component. And that's up here. We've got this little add component button. And we can search for things. So we know this is the MCP 9700. 9700. There we go. And this is the symbol I made for it. So we just drop that in. We drop as many as we want. I just hit escape. And that brings back my component picker here, and I can close that out. So I don't actually want these. I selected them with the delete key. That's how you get rid of stuff. So quick note on interface. You want a mouse. Touchpads are absolutely painful for this. Yes, you can do it. No, you won't like it. If you have a mouse, you can do things like scroll to zoom. If you click in your mouse button, you can pan around with it. If you're just using a touchpad, it's a lot more obnoxious. So zoom in here a bit. You can see we've got our 3 pins. We've got our power pin, our output, and our ground. So let's wire those up. If we go back into our components, if we go under power rails, we've got 5 volt plus and ground. Now we've got our power wired up. We've got to do something with the output of this. So I have it going into an op amp. Quick show of hands. Who knows what op amps do? Okay, so everyone but Sager's people. An op amp is a magical device which will basically subtract. It's amazing what you can do with subtraction. But different configurations of op amps can be used as summers, subtractors, multipliers, differentiators, integrators. In this circuit, I'm going to be using a basic subtractor to find how far away our current temperature is from our desired temperature. I'm going to be using a multiplier, and I'm going to be using an integrator, and then sum those two together to make a PI controller. I don't really want to get into the actual circuit I'm designing too much, since that's not the focus of the talk. But if anyone has questions about it, we can address those after. So I'm going to drop in an op amp. So in my symbol library, somewhere in here, there's an op amp. It's just a pretty generic op amp. So I'm going to need, overall, I'm going to need 4 of those. So, and if you middle click, so scroll wheel click, while you're dropping things, you can rotate. So I'm going to drop one there, drop one there, one there, one more. Hit escape, escape again. So now I've got my 4 op amps, and I'm going to need some resistors. So basic devices again, and we've got resistors. There's a couple of resistor symbols. Some people like squiggles, some people like boxes. I'm not European, I like squiggles. So let's see, we'll drop in one there, and potentiometer. we've got clockwise and counterclockwise pots. I'm going to go with this one. So I'm going to rotate that. So there are keyboard shortcuts for doing a lot of stuff, and they're really weird. The first thing that you will notice, and will trip you up for the first 6 months of using this software, is that Control-S is not saved. All of the keyboard shortcuts are sequences of keys, and they're not showing here. But save is FS for some reason. If you want to mirror something, that's EI. If you want to rotate, it's ER. You can also just right-click, and if you select and then edit, you can rotate through there. So here's our potentiometer. So if we put, I'm just going to copy paste, which is actually Control-C, Control-V. I'm going to copy paste this. So now if we turn the knob on this potentiometer, the output is going to vary between 0 and 5 volts. Rotate that. If anyone has any questions or if I'm going too fast, feel free to yell at me, stop me. It's a small enough room that people can just yell out questions. So we've got basic subtractor. For people who actually know things about stuff, you can call me out on the fact that this is not a proper dip amp. I don't care. Actually, I'm going to not use my 5 volt rail here. Op amps play nicer if you have plus and minus rails. So now we've got coming out of this, and this is the wire up here, these little blue things. So now what we've got here is, I'm just going to drop in some text to make this a little bit prettier. So we've got a set point, which is our desired temperature, which is set with our knob. We've got a temperature, which is coming out of our sensor. And then we've got our temperature error coming out of our first op amp here. So, one thing, it tries to be helpful. Whenever you see that little circle there, that means that when you drop the wire, it'll automatically connect it. That is often a really big pain in the ass. So if you hold down the control key, it'll go away and it'll go where you actually want it. Took me a while to figure that one out. It's a useful tip. So now we've got our temperature error. I'm going to stop very quickly to talk about PI controllers. Basic idea behind a PI controller is you have your error, and if you multiply your error by a big proportional or P gain, then you can use it to control something. So if you have a large error, you would turn on your heater more, and if that's not enough, then you would use a P gain to turn on your heater even more. So basically, if you, I'm going to draw the picture that everyone draws when they're explaining proportional controllers. So here's your heater power, here's your set point, here's your actual temperature. So your temperature's down here. You want to take this error and multiply it by some gain, which is usually called Kp, to get your heater power. So now you're turning on your heater, that heats things up, that brings up your temperature. Now your error is smaller, you can turn down your heater a little bit. And then eventually, if you've got the gain for your proportional gain tuned correctly, you will slowly approach your set point. You'll never actually get there because your heater will turn off when you get there, so you'll sort of oscillate below it. This is good. Of course, if your gain is really high, then instead of approaching really slowly, you'll instead overshoot it and just keep doing that, and that's bad. So there's a whole science of tuning controllers that is not the subject of this talk. But suffice it to say, that's a proportional controller. You can also add in integral. So I was saying before that you will
with just proportional, slowly approach your set point and then just kind of hover there. But if you have an integral controller, then in addition to this proportional error, you're also summing up the integral of all your error. And so if you're sitting really close to your set point, as time goes by, you're going to sum up this error. Your integral error is going to be slowly increasing for that whole time. That's going to turn up your heater a little bit more, just enough to get to that 0 point where you're exactly at your set point. If you didn't follow any of that, don't sweat it because I'm not talking about controls here today. But, so that means we're going to need a couple things. We're going to need a multiplier for our proportional gain, and that's going to be this op amp. And we're going to need an integrator for, I did it again. I don't do this much. Anyway, so we're going to need a multiplier for our proportional gain, that's going to be this op amp. We're going to need an integrator for our integral gain, that's going to be this op amp. For people who are familiar with op amp circuits, you're going to know exactly what I'm going to do next. I'm going to stick a capacitor on my integrator and a few resistors. For people who've never worked with op amps, just trust me, it's an integrator. It integrates.
I don't trust you, so.
Oh, that's smart, you shouldn't. Let's see. So, here's our integrator. This extra resistor here is just to keep it from saturating. And I could sit here and wire stuff up forever, but it would probably be really boring. So I'm going to do the cooking show thing. This is, if you go up into the menus up here, there's a page manager, and that shows all of the things you've got open right now. And I made this earlier, so just go through really quickly. Here's just a 12 volt to 5 volt power supply. It's a 7805 power regulator, a couple capacitors, and then this is the part that I already showed you. Here's my integrator. Here's proportional amplifier, summing, heater controlled by a transistor. But anyway, so a few things I did here that are probably good practice when you're making schematics. One thing is I like to actually indicate what things are on my schematic so people don't just have to squint at it. And also so I remember when I come back to it a year later. So I've got my power supply up here is in a box, a little power supply. You can add all sorts of shapes. You can add boxes. You can add lines. Don't confuse lines and wires. Wires have a purpose. Lines are just pretty. You can put it in circles. So I boxed in all my stuff and I added text using the text tool to explain what everything is. Another thing that you're going to want to do when you're actually designing circuits is usually your components are going to have values. Right now I just have a generic capacitor here. It could be however many farads of capacitance we actually need. So I can add that in. I go into right click, add attribute, use the attribute editor. There are a lot of attributes that you can give your parts. Some of them are automatically set by the part itself, things like the device, you know that's a capacitor. I'm going to set somewhere in this list is value, I'm just going to cheat value, and I want that to be, it's called a 10 microfarad, I just use 10U for micro, and then there it is, there's our value, you want to drag it over usually, make it actually visible. So here we are, we've got a pretty much complete circuit. There's a few things we still want to do. One is you'll see next to all of our components we have a letter and a question mark. And when you actually look at circuit schematics, every component has what's called a reference designator, and that's usually a letter followed by a number to indicate which component it is on the board. And usually on circuit boards they'll actually print them on the board so you can see which component is which. Makes it a lot easier to debug things and to assemble things. And you can go through and manually set your reference designators for the whole thing if you really want. Or you go up into the attributes menu, there's this fancy auto number, and it will, so you want to set it to do the whole page, overwrite existing numbers, use with caution. And then if you hit apply, you'll now see we've got this one is U5 and this one is R6, and it just goes through and does all of those. I usually don't put in reference designators until I'm completely done with the design, because otherwise you'll end up with like 600 resistors, and then you end up adding one over here next to R1, and it's R601, and it looks really dumb. So I usually don't do reference designators until the end. Let's see, other stuff. One other thing that you can do that's going to be important if you're designing for a circuit board, a lot of times when you're dealing with especially op amps or logic gates, you'll see that there are 4 of these in one chip. So right now I've got each of these op amps is specified as a separate chip, and this is using pins 1, 2, and 3, and 4. I don't know if this will work for op amps, but I just right clicked, not what I wanted to do. So right click, add attribute. Also, the window I had open there before, where is it? Oh, edit. This shows you all the attributes, and you can add and edit attributes here too. The only thing is on my computer, for some reason, the little value box is tiny and invisible, so I don't use it. So add attribute, there's an attribute called slot. Only some components have this. If you're working with actual components, you'll know anything that has more than one of whatever it is in the package has a slot. So if you have an op amp that has 4 op amps in the chip, that means it's a 4-slot package. If you're using a say a quad AND gate, that means there's 4 AND gates in the package. So we'll set this to slot 1, and then we'll see if this works. I don't know if their generic op amp has slots set, but so set this to slot 2. No, it doesn't work. Okay, and I'm just going to do an arbitrary example. So let's say you wanted to do something with AND gates. We'll go down to 74 series logic, and anyone remember what an AND gate is off the top of their head? Oh, there it is. 7408 is an AND gate, and a 7408 has 4 AND gates in a package. So let's say I wanted to wire these in together for whatever inscrutable reason. Incidentally, if you're wiring and you right-click, it'll end the current wire and start a new one. So that's a right-click there. Okay. So now I've wired these together. Let's say I don't want to use 1/4 of 4 chips. I want to use 4/4 of 1 chip. I can go in. I should really stop hitting the edit thing. So I can go in and add the slot. So here's slot 1, and you can see my pin numbers are 1, 2, and 3. It'll always default to slot 1. And now I'm going to go to slot 2, and it automatically changed my pin numbers magically. And also, if I wanted to design a PCB, I can import the schematic into PCB, and it will know that these are all the same chip. If I set the reference designator, I'm going to do the same. So if I made this U1, U1. So now what I've done is I've said that these 2 are actually part of the same chip. And I can continue doing that up to slot 4 on this. So that's slotting. So now you've got a schematic. Let's say you wanted to show this off to somebody. Say you have to hand it in for homework or a recitation with a mustachioed professor. And your mustachioed professor doesn't use gSchem, he needs another format. So there are a couple things you can do. One is it will export images in PNG, bitmap, JPEG. I've never heard of an ICO, but it'll do it. The only problem is these tend to be either huge or so pixelated you can't read them. So what I like to do is you can print to a PostScript file, which is the file that is used by printers. It's a weird file, but if you print to it, it will create a file. And there's, you can really see it there, but you can choose where you want to save it. It creates a .ps file. .ps files are kind of strange and obscure and nothing opens them, but Ubuntu and probably most versions of Linux have a built-in utility for dealing with that. And now I'm going to start talking about Linux. So I just opened a terminal. You can get to it from your little start menu here and just search for terminal. This is what most people think of when you say Linux.
Control-Alt-T.
That's a shortcut.
Yeah.
What is that? I'm not convinced that that works on all. No. Maybe in no. But anyway.
No.
So here's our terminal. It is scary and command prompt. So I'm going to run through a couple of quick Linux terminal commands just so that you're familiar with them. When in doubt, help tells you a bunch of stuff, not really useful. If there's ever a command that you're not sure of, I'm just going to include this. Whenever there's a command you're not sure of, you can type in man and then the name of the command. So the first command we're going to use here is cd, which is for change directory. So let's see what that does. Aww. You can also do info cd. But anyway, so we're going to change directory to, what did I call it? This is SparkTalk. So SparkTalk. And then if I hit ls, that's going to list the stuff in my directory. So you can see the SCH file is the schematic file that I made, and this is the PS file that I just made by printing it. So you can convert a PS file to a PDF, which is useful, and people like PDFs. There is a program called PS2PDF, I think it's 14. Yeah. Incidentally, if you ever are not sure about a command in the terminal, you can just mash tab a couple times. It'll give you a list of everything that is possible based on what you've already typed in. So PS2 PDF 14, and then give it the PS file, which is temp controller .ps, and now if I list, I also have PDF. Yay, we can email that to professors and they won't hate us. So that is the very bare bones basics of making a schematic. Let's say you wanted to do something different. Let's say you don't want to just use the basic components in the library for gEDA. Let's say you have an exotic temperature sensor that you found on the internet and you wanted to make a schematic for it. I already did that with this symbol. So I'm just going to run through how to make symbols very, very briefly. So symbols are made right in the program, just like schematics. So you open up a new one. This time you definitely have to get rid of your title block. And you're going to just draw what your schematic is going to look like. So zoom in a bit. Oh, you can change. Right now my grid size is 100 mils by 100 mils. Mils are an obscure unit. They are 1/1000th of an inch. So each of these little grids is 1/10 of an inch. You can change your grid size by somewhere in here. I don't remember. But you can also hit the brackets on your keyboard. So that's 50 mils, 100 mils. It changes the size of your grid. And since everything you make is going to be constrained to your grid, that does actually make a difference. Yeah, I'm snapping to the grid points. So I'm going to make that little temperature sensor. So I'm going to start with a box, and then I'm going to add some pins. We have 3 pins, which we can see here in our little drawings from the data sheet that we got off the internet of the thing we're going to buy. So we've got a VDD, which is our power pin, a Vout, which is our output, and ground. So I'm just going to draw in those pins. So I'm going to add pin. Pins have 2 ends. Pins should always be 3 blocks long if you've got 100 as your grid size. The red end goes out, the white end goes in. The red end is what you're actually going to connect stuff to. So I'm going to drop in my 3 pins. Oops. I'm just going to rotate this one. So I've got 1 1 pin, 2 pins. I keep putting these backwards. Okay, 1 pin, 2 pin, 3 pins. So I put my power pin on top because it's really easy to wire power into the top. Put my output on the right. You should always put your outputs on the right, your inputs on the left. You do not want schematic symbols to look like actual packages. So your actual package for this sensor is going to either look like this, or it's going to look like this, or it might even look like this. You don't want to design your schematic symbols around the physical design of your chip. You want your schematic symbols to be logical for someone who is thinking of data flowing in and out of the block. So you want your inputs on the left, you want your outputs on the right. I like to put power on top and ground on bottom because, again, it makes sense to me, and I just lost my thing. There it is. Okay. So now we've got these 3 pins, but we're going to have to label them. I just rotated those. I hit ER because you don't want sideways stuff. So we're going to have to go into the editor here. Every pin needs a few things. It needs a pin type, it needs a pin label, it needs a pin number, and it needs a pin sequence. Why it needs both a pin number and a pin sequence, I don't know, because the values are almost always the same. And we can get this from our data sheet. Pin 1 is our power pin. So this is our power pin up top here. The pin type is going to be, I think it's called POW, no, it's PWR. There's a list of these, and I've got a link on my last slide of the acceptable names for pin types. The label, they call it VDD, so we're going to call it VDD. Pin number, pin sequence, and that's pin 1. I think pin 2 is ground. No, pin 3 is ground. So we'll just make a ground pin. 3. If I'm going too fast or if I'm making no sense, please stop me. This is going to be another power pin. And the out. This is going to be an output. And this is pin number 2. So that was easy. There's a few other things that we need to do, and these are a little bit more complicated. Now we've got something that looks like what we want, but it won't actually do all the things we want. There's a lot of hidden information that if you're going to be using this stuff, especially with the PCB program, which I don't have time to talk about today. I'm hoping I can line up a talk on someone talking about using gEDA's PCB program. I'm not really the one to talk about it, but feel free to mess with it yourselves. There's stuff on the internet, and I will put links in the YouTube video once it goes up. Where was I? Oh, other things you need. So you're going to have to add a few more attributes. One of them is the device. That's the name of the device. This is the MCP9700. You don't want this to be visible. Another thing you're going to have to add is the footprint. This is the actual physical shape of the device. And this package is called an SOT23. Let's see. Oops, didn't want that to be visible. I think there's a couple other things I'm missing. There's a list of all the things you need in a Firefox. There we go. There's a list of all the things you need in a symbol on this document here, which I'm going to also link in the YouTube video. So once you've got all that done, there's one more thing you have to do, and that is going to be, where is it? Go into the edit menu, click symbol translate, and that will just move everything over to 0, 0, so that when you drop it in your schematic, it doesn't drop like way off center from your mouse. And then you just want to save as, make sure you change it from a schematic to a symbol. I like to keep all of my symbols in a directory that I call gEDA, and then I have a subdirectory for symbols. And then I can just keep all my symbols there, so you can see I've got a few. And if you want to use symbols in a project, there's some things you have to do. So gEDA, like all open source projects in Linux for some reason, likes to use text files for its configuration. So if you're working on a project where you are going to be using symbols besides the ones in the default library, the default library is pretty good. If you're just doing basic stuff, anything you're doing for Engineering 210, anything for 245, most of the stuff even in Larry Lab, you're not going to need anything outside of the basic library. But if you want to define your own symbols, then you're going to need to show it where you're keeping them. So these are the symbols that I've made over time. And in order to do that, you need to create a file to show it. So in the same directory, so this is sort of my project directory for this temperature controller I made. So there's a file which is called GAFRC. Why is it called that? I have no idea. But this is sort of your project file. You're just going to edit it with a text editor, and this is what you're going to put in it. You're going to put in component library. This whole thing is in parentheses. You're going to put in the absolute path to it. So that is my home directory /gEDA/symbols. And then you're going to give it a name, symbol library. And now every schematic that I create and save in that directory, when I go to, where is it? When I open up the component library, I have my library here of symbols, and that's every symbol in that folder. So there's the MCP 9700 that I made earlier, a few other things that I've made for other projects. So that is making custom symbols. I know I'm really blowing through stuff here, so seriously, if anyone's got any questions. But yeah, so some useful resources. One is the main website of the gEDA project is geda-project.org. There's a wiki there which has some basic tutorials, some more information. This one is the big one. There's a community of people out there who use this software. They've been making symbols, and just as important for if you're getting into PCB stuff, they've been making their own PCB footprints. 9 times out of 10, if there's something pretty simple and basic that is not in the standard library for gSchem, just search for it on gedasymbols.org. You'll find it, and you can just download it, put it in your symbols directory. Let's see. These are the rules for making symbols that I described before, and the list of standard PCB footprints for setting the footprint for your custom symbols. So that's all I've got prepared. I can talk about other stuff, and I can also answer questions. So does anyone have any questions about making schematics with this software, printing schematics with this software, saving these schematics, questions about Linux, questions about using this to make PCBs? Yes?
How would I install this on my Mac?
Okay.
I found a web page that might be able to help you.
I will hopefully get a link up to said webpage as well.
Okay. You want me to?
Actually, yeah, if you want to just, can you read it off? Is it an easy URL?
Yeah, it's pretty simple.
Okay. Installing on a Mac.
Note that it's system 10.6.8. If you want to. It's loaded on the web page, but it's a little bit different if you're installing on your Mac. Alright, so it's NICHOLS labs/author/admin.
Labs/author.
.com. Sorry.
/admin. Repeat that?
Admin.
Admin. So those are instructions for installing on a Mac.
So I can try to help you get the prerequisite software installed if you want.
Yeah, I know there are a couple of people on campus who have been successful getting this to run on a Mac. So if anyone has any problems, feel free to shoot me an email. I will get you in touch with helpful people. So So my email. My email is esda.case.edu.
Can you upload this presentation somewhere?
This presentation, the video will be on YouTube shortly. I will try to get the PowerPoint posted somewhere, and I will also try to get the Ubuntu disk image hosted somewhere. If anyone wants live CDs, got a stack. All right, questions? Yes.
Yeah, so I'm still kind of picking these things up. But once you make your schematic on the software,
Yeah.
how exactly does that translate to
To a circuit board?
Yeah, to the PCB itself.
Okay, I'm not going to go into any real detail on this because it is a talk in and of itself. But in addition to gSchem, there is a program called PCB, which may or may not be installed on this system. Maybe it isn't. I'm going to very quickly install PCB. I had to.
Oh, is this in the software center?
Yes, it is all in the software center. So if you are
Awesome.
already a Ubuntu user and you search for gEDA, there it is. This is the schematic editor. This is a tool for importing schematics into PCB. There's a little bit of wizardry that you have to do to get PCB to accept your schematic, which is why it takes a whole talk in and of itself to explain how to do this. But there are things on the internet, and if you go to the main gEDA website, you can learn about that. So this is the PCB software. You can actually just, without even making a schematic, you can just start dropping in components. If you open up the library window, if you wanted to, you could just on the fly make a PCB. So let's say, so we've got any good ones here.
Burns probably has, or I guess maybe Burns probably has that pot you had on there.
So if I want to say make a quick PCB with just an LED on it, a couple LEDs maybe, and then I can start wiring them up. But if you make your schematic in advance, then it will, first of all, it will drop in all your components for you. Second of all, it will make what are called rat lines between all of the things that are supposed to be connected. Rat lines are just little sort of air wires between things that should be connected, so you know whether you've connected the right things, and then they'll disappear as you add them. So a finished PCB would look something like, so here is, I'm going to show you, this is a PCB I made for part of my master's project. It's a two-layer board. So here's just the one layer, here's the bottom layer. And I made this from a schematic. That looks like, which was that? Was that the
Breakout.
Oh, it's breakout? Okay. So I made the schematic, and then I imported it into PCB, and then actually laid everything out. In the real world, this is the process. If you're working in industry, designing printed circuit boards, they will have you do schematic capture, and then they will have you lay out the PCB. A lot of people who are just sort of amateur houring it as hobbyists will go straight to PCB design, maybe using some chintzy little web tool that's free from some PCB board house. There's advantages to doing things in schematics first. It means you've actually got documentation of your work, and that's why everyone in the industry does it. Second of all, the schematic is capturing something that is different from the PCB. The PCB is a particular instantiation of the design. This schematic design exists independent of the printed circuit board. There are thousands of ways that I could lay out this board for different applications, but it would still have the same function, and that's what the schematic captures. So in short, I didn't answer your question because it would take several hours. But yes, there is a PCB tool. It is a little bit clunky, and there's definitely a learning curve to it. I can tell you I spent a couple of months learning how to do it while I was designing these boards. If you're just doing something simple, it's not that hard to use. Obviously, as the complexity of whatever you're doing increases, it's going to be harder to do it. It's not as nice as working with, say, Altium, but again, that's the difference between $3 and $5 grand. Any other questions? Is there anything that anyone else wants me to talk about? One thing I do want to make a plug for, there is a website called GitHub. GitHub hosts, shut up, Andrew. GitHub hosts Git repositories. Git is a tool for version control. So if you have files of code or documents, or in this case, schematics of what you're doing, you can use Git to keep a history of the versions, revert things back when you mess stuff up. The nice thing about Git is when you use Git with a Git server like GitHub, you can share things with people. So when I took ESIS 371 last year, my lab partner and I set up a repository here on GitHub, and we just kept all our labs in here. And we used Git to, whenever one of us did something, we would use Git to upload it to this site, and then the other person could pull it down, make changes, and we could share files that way. Yes?
So is it kind of like Google Docs for this stuff?
It is it's sort of like the Google Docs Dropbox model, but it is more powerful and a little bit less idiot-proof. It was originally designed for sharing code, so it's optimized for plain text files. But the nice thing about it is every time you commit something to your repository, you have to have a message. So then you have this nice history of everything you did. So this is every time I committed something, I had to put a message, and then I can look at everything that was in that. And it's not that helpful looking at the raw text changes of these files, since that's not very informative. But if you were doing text files, it would obviously be more useful. We just used it because we both had experience with Git. But the reason that I'm plugging GitHub is because on GitHub, we have a recently made group. So if you go to github.com/CWRU-EE, all caps, hopefully it'll load soon. There's a couple of useful repositories here. And so if you want a whole bunch of gSchem symbols, gEDA PCB footprints, I'm trying to get some Eagle symbols and footprints up in here for people who use Eagle, and also for anyone who uses LT-Spice. LT-Spice is a circuit simulator. We've got some libraries for that. I'm looking to grow these, so people who use any of this software, if you've ever made your own footprints, your own symbols, or your own LT-Spice models, let me know, and hopefully I can add to these. All right, that is all I've got. So if anyone has questions about anything, feel free to either ask me after or email.